This will be an example of an SN1 reaction. And this is from one of the examples from the list in Blackboard, which is called Synthetically Useful Substitution and Elimination Reactions. And this is an example of reaction 1. So this one here, we see that we have a secondary substrate because here at the alpha carbon, there are 2 carbon atoms bound to that alpha carbon. We see we have HCl as the reactant. And in determining if we think this is more likely to go SN1 or SN2, one of the things we notice about this is that we have, an okay nucleophile here, or, pretty good nucleophile here in terms of the chloride anion. However, it's bound up in HCl. So the first thing that's going to have to happen here is we're going to protonate this OH group. And the main reason for this reaction is to convert this hydroxyl group, which is generally a bad leaving group, into the alkyl halide, which has a better leaving group. So often this reaction might be done first before whatever else it is that is desired to be done, at this site. So first we convert it maybe to a better leaving group, and then we do another reaction with it, which might seem like a waste of time, energy, effort, doing 2 steps instead of just 1. But depending upon exactly what we're trying to do, it might actually end up being more efficient. So again, it would depend upon the exact reaction and how each one of them works. So here, the very first step in the mechanism, I'm just going to list this out here, will be the proton transfer. So we're going to protonate the alcohol. And this is a kind of a classic first step if you have an alcohol or something like that present, or maybe even an ether, and you have a strong acid present. This oxygen here is going to be relatively basic compared, of course, to the HCl. So let's go ahead. I'm going to draw out the mechanism down here below. And again, we often like to expand the reaction site when we start drawing out a mechanism, because we want to make sure that we're keeping track of things. Here it makes sense that this might happen because of the partial charges on the HCl. And of course we are aware we have a partial negative on that oxygen atom. So again, the first step will be proton transfer. Okay, so now we have our protonated alcohol. So this was an alcohol. Now we have a protonated alcohol. And we do have chloride anion now present. We made that as the byproduct from the HCl. And so here is kind of where we have a decision point. So some of this might go SN2 because this is a secondary substrate. So it's probably going to be a mixture of some SN1 and some SN2. So we can go ahead and draw both. So I'll go ahead and do SN2 in purple. And of course what we expect there is the inversion stereochemistry. So the water leaving group comes off, and the halide attacks on the opposite side. So since this is on the wedge, the chloride, when it comes in, will be on the dash and will be opposite side of that. Sometimes when you're doing a problem, the answer key or whatever might have it drawn in a slightly different way, but you can always assign RNS as long as you can do that accurately. To double check that your configuration and what's in the answer key, so to speak, are the same. So that would be the SN2 product. Now the SN1 product, of course, if we do SN1, that's going to be heterolysis followed by coordination. So first we'll undergo the heterolysis. I'm going to draw this in red. So this would be, oh, somehow my wedge got erased. Let's fix that. Okay, so, oh, goodness. All right. So heterolysis would be just that bond breaking. And we've lost our water, and now we have this secondary carbocation. And we know the secondary is better than primary. However, it is a carbocation, so we do need to check for rearrangement. So when we check for rearrangement, we see that if we did do a hydride shift here, we would end up moving one of these hydrogen atoms, one of the hydrogen atoms from the next carbon over to the right. And then our carbocation would be here. And some of you may be thinking, well, that's also a secondary carbocation. However, it's not just any secondary carbocation, right? There's something we can do with this. We have a positive charge right next door to a pi bond. So we can do an allylic cation pattern. And when we do that, we end up with a second resonance structure. So this is going to be resonance stabilized, where our hybrid would look like this, and that partial positive would be spread out over these two atoms here. I think I'm missing a carbon atom. There we go. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so this is really what we're looking at here. And now the nucleophile can attack at either of these locations. Now, this is still secondary and this is primary. So this resonance structure on the right is the more stable, meaning that you'd have a larger partial positive on that carbon than you would on the other carbon, because this one is secondary and the one on the left is primary. So that means that's where the nucleophile is going to attack here. So this will be the coordination step. And so now we have the chlorine here. And again, the chlorine, because this is trigonal planar, it can attack top or bottom. So we're going to get both this one. Here, let me draw it to the left to give us a little more space here. And this one. So a lot of times what I'll do is just to kind of save a little bit of time, and sometimes you might be asked to draw both stereoisomers, and then obviously you would need to draw them both. But a lot of times on paper or on tests, what I would do is say plus EN. And so then all you have to do is just draw the compound plus the NA2 and say plus EN. This would, of course, be a racemic mixture. So optical rotation would be 0. And so let's up here draw the products that we would get. One way to indicate uncertainty in stereochemistry is to draw like a squiggly line here. And that generally indicates that either stereochemistry is not known or maybe it's a racemic mix. So you could do that, or you can say this with a wedge or a dash or whatever, plus EN. And then we would get some of that inversion product from the SN2 reaction. Okay, so those would be kind of the mixture of products we would get. Because of the rearrangement here and that allylic cation setup, I suspect we would probably get more SN1 than we would SN2, and that would be the favored product. But it is a little tricky to tell. Another thing to notice here is that this SN1 mechanism kind of gave us a little bit of a mess, right? So we get the rearrangement, we get some of the SN2 product. And so oftentimes what we try to do in a synthesis is to target just the SN2 mechanism, because with that we can control the stereochemistry and rearrangement is not as likely. But sometimes the SN1 is fine, sometimes it's not chiral, or it's not going to rearrange, or maybe we want the rearrangement product. So sometimes the SN1 is fine as long as we understand the things that can happen along the way with SN1.